All right, this video is about using series. This was like Taylor's series to help solve differential equations. The focus of what we're going to be doing mostly is solving differential equations that we already know how to solve in other ways. But that's mostly just because it keeps things simple for us and we can see how the process is. But by the end of the next session, we will have a problem that will be something that is hard to solve, and the series gives us a fine way of getting an approximation to the solution, okay? So we're going to start off with an equation that is real simple. What if I had the function y is e to the x? We know the derivative is also e to the x, so I can make a quick equation out of this. Y prime minus y is just 0. They're the same things, right? That's a differential equation. It's an equation that relates a function and its derivative in some way. We know that y equals e to the x is a solution because we just sort of made it up based on what we see. Now, let's go backwards though. What if I just were given the equation y prime minus y equals 0, and I was asked to solve, like, give me a solution to this equation. How do I go about that? And again, I'm assuming that I don't know that work above. Again, differential equations talks about ways that you can solve this. You can do some integration things and whatnot. We're going to skip that. We're going to go towards a series solution. So how can we do that here? And one thing is we could say is, well, this function, my unknown function, has a Taylor series. And for the purposes of this class right now, we're going to center all of my series at 0. So my series has, or my function has, my unknown function, by the way, make sure we're clear on that. I don't know what my answer is. It has some sort of series, Taylor series, which is f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2x squared plus f triple prime of 0 divided by 3 factorial times x cubed plus the fourth derivative of f evaluated at 0 divided by 4 factorial times x to the fourth plus dot, 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 dot. It keeps on going. But we don't know what f of x is. So I don't know what f of 0 is or f prime of 0 or any of those things are. So at first we're like, well, how can I do anything? I don't know what any of these variables are. I don't know what the function is. But what I'm going to do is I'm just going to give each of those coefficients a name, like a0 and a1, a2. So a0 is just f of 0, which I don't know. a1 is f prime of 0, which I don't know. a2 is f double prime of 0, which I don't know, etc., all the way through. And so I can write this now as y is a0 plus a1x plus a2 over 2x squared plus a3 over 3 factorial x cubed plus a4 over 4 factorial x to the fourth. Now, if I know what all the a's are, a0, a1, a2, a3, if I know what those are, then I can approximate what my function is, or I even know what exactly it is. So I'm going to see what I can figure out. Well, now, if I know what y is, and it's this thing here, I can take its derivative. Y prime, well, the derivative of a0 as a constant is just 0. Derivative of a1x is just a1. The derivative of a2 over 2x squared, well, the 2's are going to cancel out, and I have an a2x. Plus, derivative of this term right here is going to be, well, the 3 divided by 3 factorial, the 3's will cancel out. I'm left with just a 2 factorial, or a 2. So it's a3 over 2x squared. And then take the derivative of the fourth term, and you're going to get a4 over 3 factorial, x cubed, and so forth. So write out all those terms if you need to, and take some derivatives and see how it all works out. See how the factorials interplay with those coefficients coming down and whatnot. So now if I'm told that y prime minus y equals 0, then, well, here's the y prime part minus the y part, and that's equal to 0. Now let's collect and combine like terms. All right, my constants. The constant here is a1. The constant over here is a0, so I have an a1 minus a0. I have a linear term here, a2x. Linear term over here is a1x, so that's a2 minus a1x. The quadratic term here is a3 over 2. Quadratic term over here is a2 over 2. So I have a3 over 2 minus a2 over 2 quantity times x squared. And then the cubic terms, I can see those. Well, that one's not written out here, but it is here. I have a4 over 3 factorial minus, come up here, a3 over 3 factorial x cubed, plus it keeps on going, and all that's equal to 0. Well, right-hand side is equal to 0. well, for you, the right-hand side is equal to 0, which means all of this stuff must be 0, which means all of these coefficients must be 0. And so from right here, I know that A1 must be the same thing as A0 or A0. This tells me A2 must be the same thing as A1. There's some divide by 2 step, but at the heart, A3 is the same thing as A2. And at the heart of this, A4 is the same thing as A3, and so forth. Oh, wait, everything's equal to everything else. A0 is the same thing as A1 equal A2 equals A3 equals A4 equals what? What are these things all equal to? Well, it turns out that differential equation is not enough to guarantee a unique solution. I need more information. I need an initial value. Tell me something about the function that we know. There are infinite solutions as is. So let's just say that one of my initial conditions could be that f of 0 is equal to 1. That's just my initial condition. Well, f of 0 is the value of A0. So that means A0 is 1. It means everything is 1. All the coefficients are 1. So if I go back to the original equation here, turn all of these A's into 1s, and I write it out here. Y is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And if you remember, that's the Taylor series for e to the x. Oh, I just found the solution that I already sort of knew existed. Great. But what if I picked f of 0 is equal to something other than 1, like f of 0 is equal to 5? Well, that means all of my coefficients are equal to 5. So then y is 5 plus 5x plus 5 halves x squared plus 5 over 3 factorial x cubed plus 5 over 4 factorial x to the 4th. Everything has a 5 in it, which means I can factor out a 5. Factor out a 5, I have 5 times 1 plus x plus blah, blah, blah. Oh, in parentheses, I have e to the x. And again, I have 5 times e to the x. Oh, yeah, that's right. When I think of a function which is the same as its derivative, I always just think about e to the x. But the truth is that 5 times e to the x also is equal to its own derivative. Y prime is the same thing as y. And I can do one more initial condition. I mean, there's lots of them that we can do, but there's one more that we're going to do. And that is, what if the initial condition f of 0 is just 0 itself? Then 0 is equal to A0, which is A1, which is A2, so forth. Oh, all the coefficients are 0. That's just the 0 function. Oh, yeah, if my function is the 0 function, then it's also equal to its derivative. So in general, I have found that the solutions to y prime minus y equals 0 look like y equals some sort of constant a times e to the x, where a could be 0. And if not, it's just some other constant, 1 or 5 or -3 or whatever it's going to be. All right, so that's our initial example of looking at taking a differential equation, thinking about its series expansion, and then using that to try to solve or at least approximate the solution to the differential equation. This video is going to stop here, and then we're going to start a new video for the next example, which is on the next page.